Hello, welcome to the subject microcontroller. This is Professor Meenakshi Pancha from Electronics and Telecommunication Department, Parvatibai Ganma Music College of Engineering, Wabuli, Pune. In previous lecture, we we are going to discuss. In today's lecture, we are going to discuss about some few programs, how the LEDs are interfacing with our 8051 microcontroller. So this is one of the small example. Let's see. Write a assembly language program to blink 4 LEDs continuously, which are connected to port 1. Here the 4 LEDs. Here 4 LEDs which are connected to the port 1 of the microcontroller. The pin number P10 to P1.3. For these 4 pins, the 4 LEDs are connected here. These 4 LEDs are connected here, and we have to blink these LEDs. We have to blink these LEDs continuously. We have to blink these LEDs continuously. For that, we have to write a assembly language program. So first, we have to start from flowchart. First, we have to understand what are the logic and how we can perform step-by-step operation here. First, we have to start. We have to configure all these pins where we have connected and LED pins, make it as a output ports, and put put all the LEDs off. So how we can perform this by using accumulator. Load the accumulator A with the value 0, and after move the accumulator value into the port 1. Hence, the 0 will be loaded into these ports. It means all these ports act as the output ports, and due to 0 signal, all the LEDs will be remain off. And after that, for we have to wait for some time. So hence we will call one subroutine program, or we have to write some subroutine for the delay purpose, and we can call that subroutine by using call delay. After calling delay, what will happen? We should do? We should load the accumulator with the high signal and move that high signal using accumulator to these ports. So what will happen here? The accumulator accumulator having high signal. So we are loading accumulator to these port. So these port will become high. Then due to high, this port will provide provide voltage to this LED. So due to that voltage, all the LEDs will become glow. So after 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 turning on these LED, we have to wait for some time. So that's why we are again calling here call delay subroutine by using a call instruction. Then after call instruction, we have to again turn off these LED, because our main task is we have to blink the LED for continuously. So once starting it was off, then it become on. Then after some time delay, it should become off. So LED should be turned off. So this same task should be performed continuously. Hence, we are doing the same task by loop operation. By loop operation, we are doing same task repeatedly. So such flow, we have to write command. See here. Come here, programming here, assembly language programming here, org, that means starting the program at particular memory location 000H. We are going to start writing program from 000 memory H 000H memory. Then we are writing instruction like move A, 0H. Move A, 0H means the 00 immediate value we are loading into the accumulator A. So which will makes, why we are doing like that? Because we have to make port 1 as an output port here. So this A value will be loading into port 1 by using the instruction move P1 comma A. Move P1 comma A is nothing but the value inside E00, that is loading into the P1. Now P1 is loaded with the 0. So hence the port P1 is 0 loaded, hence it will act as the output port, and all the LEDs will be turned off because there is no current flow through this. Still there is no current flow through the pins of the port. After that, we are going to call a delay by using a function call. Sorry, we should not write like a. We have to write call delay. We have to write call delay. A should not happen here. This is only call delay. So call delay is nothing but where is the delay here? Delay is here. So after executing this instruction, the program counter will come here and start executing from here. So what is in delay? In delay, we are taking two register R2 and R4 and R5. In the R5, we are moving the value, decimal value hash 225. So hash 225 immediate value we are loading into the R4. Then after executing this instruction, what will happen? It will move again R5 to 50. So after that, what will it comes here? Then what will happen here? It will decrement XEM non-zero to R5. So it will check the value of R5 if value of R5 is 0 or not. So if not 0, it will decrement by 1. Presently, there is 255 value is there. It will decrement by 1 and check the result 254. So this is not equal to 0. If not equal to 0, it will go to here. Where is here? Here is there. It will perform same operation until the R5 will become 0. So now R5 is become 0. Then what will it will comes here now. This instruction will be executed and it jump to next instruction. The next instruction is what is there in the next instruction. The same operation will be performed in this instruction. It will check the register value R4 and decrement by 1. So what is the value inside is 250. 250 minus 1. So it is nothing but 249. So is R, it will check R4 is 0 or not. No, R4 is having 249 value. Now this is, it will not come to execute next instruction. It will go to here repeat. So here repeat operation here in this task it will come. So same operation will be performed here. It will wasting the time here. So after some time it will all the values will become 0. R4 and R5 will become 0. Hence then R4 also become 0. Then it will execute the next instruction return. So after executing next instruction it will come here. Then it will move P1 comma A again. So we have to load here. So another instruction we have to write here move A comma hash 0fh. 0fh. We have to write this instruction first. After executing this instruction, A should be loaded 0fh value. After that, move P1 comma A. Now A having 0fh, then that 0fh value will be moving into A. So the 0fh value moving into A is nothing but this pin will become high. This is, and the other pin will become 0. So this is nothing but 0. F111 is nothing but F. So 0, 0FH. So after getting this 0FH value, the LED will become on. The LED will become on. Now we have to wait for some time. Again, we are going to call this subroutine delay. Now same operation will be performed here. Then after some time, it will come to S jump. Where is the S jump? Jump to this loop. So again, it will come here, this loop. So from starting, the same operation will be undergoes here, on and off, on and off. So this is the small example writing the assembly language program for blinking 4 LED. That LEDs we have connected to port 1 pins. Now let's see how the delay will be calculated. In previous problem, we have called the delay. So what value, if for example, we have taken the R4 and R3 value is we are loaded some value like that immediate value hash 255 and 250 we have loaded like that. So at what amount delay will be produced there? So we are going to calculate such type of delay here. So in this section, how we can calculate the delay? So here we have to first we have to think the instruction cycle about the instruction cycle. So what is the instruction cycle? That is and how in this section we will see execution consists of fetching the instruction and decoding the instruction and executing the instruction. All these things will be happen here. So at what time should be required for completing these tasks for fetching, executing, decoding? What time should be required? So that time is called instruction cycle. The time required for completing the total execution or whole execution of instruction by the microcontroller is called instruction cycle. The total time required for completing some particular instruction, that time is called as an instruction cycle. The instruction cycle consists of many machine cycles. We have seen in first unit. I have drawn in clock oscillatory at that part. I have explained with the diagram. Each machine cycle will consist of 6 states and each state consists of 2 clock pulses, so that complete machine cycle will consist of 6 states and 12 clock frequency. 12 clock frequency. So 12 clock pulses, sorry, 12 clock pulses is there. So the machine cycle, what is machine cycle is nothing but time required to accomplishing any simple instruction or a complex instruction is called machine cycle. Some part, if there is a program, a particular instruction or some complex instruction like a subroutine, we have seen in the last time delay is providing. So calculating that time for the execution is called as a machine cycle. So machine cycle may be opcode fetch the memory or read the memory and write and read. All the operation time can be calculated or performed using this machine cycle. It will fetch. Then machine cycle made up of 6 states. I have told that the machine cycle have a 6 state. Each state has 2 clock pulses each machine cycle has total 6 states. One machine cycle is nothing but 6 states here. See, one one machine cycle that is equal to 6 states. 6 state and one state that equal to 12 pulse. 12 pulses like see here. I have explained. See, these are the clock pulses. These are the clock pulses. Each starting 2 pulse. This one starting, this one starting. This is having one state and one starting pulse, one starting pulse. This is having second state, and like this there is a total how many? There is a 6 state and each state consists of 2 pulses here. Each state consists 2. So this is one complete machine cycle. So one machine cycle how many? It will having 12 pulses and 6 state or 6 state. So how the time is required for executing a particular instruction, we have seen there is a one formula. The time to execute an instruction is C into 12 by F. C into 12 by F. Here C is nothing but number of the cycle of the instruction and 12 is the 12 pulses and F is nothing but crystal frequency. At what frequency is generated inside the our microcontroller is operating at what frequency? That frequency will be considered here. See, if this is the one of the example here. Here, our C, there is a one machine cycle, our C is 1 and our clock frequency is this much 11.0952 megahertz at one machine cycle. So we have to calculate here what time should be take to execute one machine cycle instruction. At one machine cycle instruction, what time should be execution time should be required and our frequency is 11.09 and one machine, this is a formula, this is same formula here. One machine cycle is required. Here is nothing but C, 12 into C. Here C is 1 because machine cycle is 1. So one machine cycle divided by F. F is here our frequency. So time required for completing one machine cycle we are calculating here. So F is our frequency, this frequency 11.095 megahertz. So for executing one machine cycle at this frequency, this much of time is required. So such kinds of the example they may be asked in the example, they will give at certain frequency and they will ask time delay or what time required for executing the instructions. They are also maybe give some instructions there. See, if they have given like that, so what we have to do, we will see here. We have to keep it in mind. There are some instructions, they will take 1 to 4 machine cycle to execute the instruction. For example, move, comma, R3, comma, hash 55. So such kind of instruction, they will take one machine cycle. So this means one, how much time they will take. For example, this kind of instruction, it will take one machine cycle to execute. Total one machine cycle, it will take a execute this instruction. So total what time is taken to execute this instruction is nothing but one machine cycle into and the amount of time at this frequency. At this frequency, what amount of time? So 1.0585. So this is the amount of time that is equal to say 1.085 microsecond will be take. At this frequency, at if our microcontroller is performing some operation, executing such instruction, it will take one machine cycle. And at what frequency our microcontroller is going to operate, this frequency 11.095, at this frequency it will going to performing some operations. So we have according to this frequency, the time is required. How much time required? 1.085 time is required for executing the instruction one machine cycle. So one machine cycle is nothing but 1 into 0.085. So total 1. Same amount of time should be required for executing the instruction. For example, such instruction decrement R3. This is also, it will also take one machine cycle. This is 1 byte instruction, so it will take one machine cycle. And same here. Ah, one minute. So this instruction, the same 1 point, so 1.085 microsecond time will be taken. So we have to consider all the instruction, how, what type of, and what amount of time it is taking. See, in the example, they may give such type of instruction, and they will ask the what are the time required for execution this instruction with a particular frequency. Here the frequency is 11.095H. First we have to uh, consider. First we have to calculate at this frequency what amount of time required to execute particular or one machine cycle. So using this formula, we should calculate the time required for one machine cycle. Time required for executing one machine cycle. So first see here, such type of instruction is there. For example, move R3, hash R5. This is immediate data we are transferring into R3. Such type of instruction will take one machine cycle for execution. So this is nothing but 1 into particular time delay is nothing but same. The 1.085 microsecond is required for the execution of this instruction. If for example they have given decrement R3, this is 2 byte instruction. This is also 1 byte instruction, and it will take same 1.085 microsecond for execution of this instruction. See another instruction. This is decrement jump non-zero of R2 is a at the target, whatever the value is there here, jump if the R2 value is 0. If not 0, it will decrement. So this is 2 byte instruction which will take two machine cycle for execution purpose. So the time required for executing one machine cycle is 1.085. So total time required for executing two machine cycle is nothing but 2 into this much. So 2.17 microsecond time is required for executing this instruction. Similarly, ljump is also 2 byte instruction which will take two machine cycle for execution, and sjump also, which is also take two machine cycle for executing the instruction. So knob will take one machine cycle, and here see the multiplication operation multiplication A and B will take 4 machine cycle for performing the operation, which will take 4 machine cycle. So 4 into 1.085, that's equal to, so that is equal to 4.34 microsecond. So this is the way how the time execution we are going to calculate. They may be asked particularly in the examination, and they may give the frequency, and according to that what is the time required for executing this instruction they may be asked. So you guys should be practice such type of formula so you can answer very well in the examinations. Let's see another example. find another example. We have to calculate the delay for execution time. We have to calculate the now there we have find the time required for executing the instruction. Now they are given a total whole loop here they have given such kind of loop. Move a comma hash 55 h move port 1 comma a call delay. Call delay and C P L is nothing but complement A. What is the data inside the stored inside the A? So this is the one of the instruction and delay is started from here. Delay is one of the subroutine program here. Move R3 comma hash here decrement jump non-zero of R3 comma here. This is the one of the small program. Here they are asking what is the time delay provided by this delay subroutine. The delay subroutine is starting from here. Delay move R3 comma hash. So what time is this subroutine is providing? So we have to calculate here. So they have given frequency that is equal to 11.9 1.059 they have given. This is the frequency at this crystal frequency which is providing this much of frequency and generating clock pulses. At that clock pulses the time program will executing at particular clock pulses. So what amount of delay is providing or what amount of time is taking for executing the instruction from this to here. So we have to calculate. This is the problem. So we have to. So first we have to think what time is taking at this frequency for completing one machine cycle. For one machine cycle, what time is taking? So this is the formula. This is the formula. What is the formula? 12 into C is nothing but machine cycle. That is divided by frequency. So what we'll get? 12 into C here, one machine cycle. We are calculating first for one machine cycle. Divided by what amount of frequency they have given? 11.0952. So, one for time is taking, one machine cycle is taking time 1.085 microsecond. So, this time is required for executing one machine cycle. Here, see, this move R3 comma hash. So this type of instruction take one machine cycle for execution purpose. So this will take two machine cycles for executing this instruction. Then RET RET also take 2 machine cycle for executing this instruction. So we have to calculate. So total what time will be required for executing this command. So we have to calculate time required for this subroutine. Time delay in subroutine is time delay is equal to total number of machine cycle required, that into time for one machine cycle takes to execute. So see here, how many times the same program is executing here. See here, the R3 is loaded 200. After 200 loading, this same execution here. R3 here, R3 is loaded. R3 is loaded 200. R3 is loaded 200. The same, it will decrement 1 and start executing here. It decrement 1. If not say it not 0, then go here. Then here it will start executing same instruction up to what time? 200 times it will execute. Same execution, same instruction will be executed by 200 times here. 200 times. So it will take how many amount of cycle? 2 machine cycle will be take for executing particular instruction. So total 200 into 2 is taking this particular instruction. Then other few instruction is also there. So other few instruction. After executing this will take 2 instruction, 2 machine cycle. So this will take 2 machine cycle, and first this one is also take 1 machine cycle. So this much times the same instruction will be going to executed, and the total time is so how much time the same instruction executed? 403 times. 403 times the same instruction will be executed, and 403 machine cycle will be taken here. So what is the time required for completing one machine cycle is 8085. This much of time is microsecond. This much of time is required for completing one machine cycle. So how many machine cycle required here? This subroutine execution 403 machine cycle here taken for executing this much of instruction. So total what time is required? 437.25. So 437.25 microsecond time is required. So this subroutine for we are calling delay here. So this much amount of waiting time generation purpose, this much of time delay purpose, we have called this subroutine. This subroutine generated how much time delay? 437.25 microsecond delay. Here this subroutine will be generated. See here, in previous slide we have seen one small formula for blinking the LEDs, there are also we have mentioned this delay subroutine for waiting purpose. Once LED will be off, wait for some time. What some time? This much of time. After this much of time, then LEDs again will turn on and wait again some time by calling this delay. So this delay, and here the delay is also generated this much of time, and after that sometime there is a loop operation is there, continuously the same operation will be performed repeatedly. So this is the way of calculating the execution time of this particular subroutine. They may be also asked what is the time required, execution time required for whole program also. But in this program we have seen the how the delay will be calculated or produced by this subroutine. Let's see another program or another example how the delay will be and what amount of delay is provided by following some instructions. I am writing directly here one branch instruction or subroutine here, which is R3 comma hash 250, and here knob. See here, we are we have to calculate delay that subroutine producing. So these are the some instruction, and these operating frequency is 20 megahertz. At that frequency, the microcontroller is performing the operation, and this is the program. So we have to find out what is the delay can be generated by using this subroutine. First, we have to see what particular instruction takes how many machine cycle. This move instruction will take one machine cycle for executing this instruction, and here this knob instruction is also take a one machine cycle, and similarly this knob instruction will take one machine cycle. There are total 3 knob instructions is there, and here this decrement and jump, here this will take how many machine cycle it will take. It will take 2 machine cycles, and the return instruction will take 2 machine cycles. So we have to first calculate for what amount of time required for calculating one machine cycle first. So we can calculate it by using this formula. What's that? C. Here, this same formula. Here, this formula. Here, C is one machine cycle. So I am writing here 1 into 12 that divided by F. Here, what is the frequency? Frequency they have given. What frequency they have given? 20 mega. Mega is nothing but 10 raised to the power of 6. I am writing here in the short. Mega hertz. So 20 megahertz frequency. So total what time is required? Here 0.6 microsecond is taking for executing one machine cycle. So now we have to calculate how many machine cycle will be required for executing the whole subroutine instruction. So we have consider one by one first. See here, inside the here loop, there is two loops here. What's here? There is two loops here. One is the delay loop, another one is here loop. The here loop is inside the delay loop. So first we calculate the inside loop, how many machine cycle will be take. See, first the delay executed and it will take one machine cycle and it will load R3. It will load R3 to 50 number. So 250 number means 250 times this. So 250 times this instruction will be executed. Means each time it will take one machine cycle. Hence each time it will take one machine cycle. And after that it will come here. So it will come here. Each instruction will take executing 1, 2, 3, 4, 5 and 1, 2, 3, 4, 5, 6. After executing this 1, 2, 3, 4, 5, 6. Six machine cycle is required. So total 1500 machine cycle is required executing inside the loop. So outside loop it will take total 1500 into this one also. Here this one and after this RET come outside of the loop. Here this loop is starting from here. So this loop is repeated 250 times. So this loop is starting here. So 250, 1, 2, 3, 4, 5, 6. After 4, 5, 6, it will come again here. So it will 6 time it will take here 250 into 6. So total 150 time the loop is inside loop will be executed. So this much amount of then outside loop will be executed, and it will take 1 and 2. 1 and 2 total 3 machine cycle it have taken. So total 1503 machine cycle is required for executing this delay instruction or delay subroutine. So each machine cycle takes 0.6 microsecond for the execution. Here total how many 1503 machine cycle is there, and time required for executing each machine cycle is 0.6, that is nothing but 901.8 microsecond. Time is required for executing this much of instruction. If we called this instruction for the delay purpose, then this much of amount of delay it will generate. So this is the one of the example. So this is enough for the day. And in the next lecture, we will see how our microcontroller will be interfaced to other devices like a 7-segment display and all that. So this is enough for the day. Thank you.